To the final presentation of our session before our lunch break. The topic is software-defined network works for automotive. Will be presented by Carsten, holds a PhD in computer science and has a long history in networking and distributed computing. He has worked for 13 years and mainly on AutoSAR communication layer development for Audi projects, many of which were safety relevant according to ISO 26262. He works now with Electrobit on low-level communication software development. And the second speaker, Daniel Thiele, holds a PhD in computer engineering with a focus on formal performance analysis of time-sensitive Ethernet networks. Since joining Electrobit in 2016, his works has ranged from automotive Ethernet to cloud-based network virtualizations. Daniel's current research focused specifically on automotive software-defined networking. Gentlemen, the floor is yours.
Thank you very much for the introduction. So Daniel and me are from Electrobit, and we are going to report from a research project that we are doing since some years, where we are doing experiments with software-defined networking. And I think the talk fits very well to the very nice talk from Jodesro and Ricardo. And we are going to argue again that software-defined networking are useful for automotive and they are possible for automotive. And we also have a very concrete proposal for this intermediate step that also Jodesro was talking about, that we could use as a first introduction for software-defined networking. So let's start.
Yes, all right. So first of all, an introduction to SDN. It's a slightly different perspective than the first talk, but I think it interleaves quite well. So SDN, as we have learned, is widely used in the IT and service provider networks, where it helps the operators of such networks to customize their networks or to manage them in an efficient way. And we want to see if we can take some of these properties and also transfer them to the automotive domain. And to understand this better, first of all, we have to look at where we're coming from. So here on the left-hand side, you see a non-SDN network. You may have a couple of switches from different vendors, and what you first see is that the data plane that moves data according to certain rules and the control plane that makes these rules are tightly coupled. So that means if you want to update your network along a path, you have to individually and proprietarily basically compute the configurations of all your switches and then roll them out individually. And SDN networks, on the other hand, they basically introduce some nice abstractions to make this management easier. So the first thing you see is they decouple the data and control plane, and the data plane is designed or abstracted in such a way that you abstract from the actual network devices. So any switch from any vendor will look and feel like a switch to the SDN controller. And the next thing that we have is the network controller has a resource reservation API, and this is an abstract API where applications can basically make their resource reservation requests against, and the controller then, it's his job to basically compute this depending on the network it manages, and rolls this out then consistently, and it also can do so very efficiently because it has a global view of the network. And if you want to apply SDN into the automotive domain, we first have to learn about the limitations and constraints, and this is what Carsten will now tell us about.
So we will argue again that if you want to have a software-defined vehicle, we also need software-defined networking. So the challenges that we have now is they are all very well known. There's lots of new bandwidth, lots of new quality of service requirements. There's still safety and security requirements, and the number of subscribers is still increasing. But this is all well known and can be calculated upfront. But this also becoming more and more important is the fact that this is needs to have some flexibility. These things change a lot. There's very fast cycles of introducing of new ideas for new applications. And the status we heard that already very often in this conference. We have a very static configuration. OEMs want to have that static. They don't want to change it. And this is arguing that the traffic in the car is very well known and it's very repetitive. So no flexibility is needed. But I would argue when you want to have a software-defined networking, you also need some reserve for unknown and new traffic. And for this, you need the flexibility. So let me look at the software-defined vehicle from a certain point of view. One of the key aspects for me is the real software-defined vehicle is reached when you can add a new software on an old vehicle. So a vehicle that has been designed 5 years ago, I want to add a software that has been developed now. And the other way around, when I have a brand new vehicle, I still want to use the nice software that I purchased for the old one. So I need this decoupling of the software from the vehicle. And for this, certainly you need reserve. So if everything is full and predefined, then I would argue this cannot be really done. So we need this flexibility, we need the possibility to update the network also. And now we continue looking at how this can be done actually.
Yes, so this is an so this is a simplified architecture we envision for realizing such dynamic services as Carsten told us about. So basically, we identified 4 key ingredients or components you need for this. So first of all, you need a service discovery mechanism that is also able to negotiate quality of service parameters. So you need to communicate your T-spec, your Q-spec from the talk before, somehow as an application to state your needs. Then you need a resource reservation interface with the SDN controller to basically let it know about what you want from the network. And then the SDN controller needs an interface to make concrete resource reservations to allow these 2 applications to talk. And then if this is all successful and propagated back, your applications can finally talk. And now there's a couple of interfaces involved. The service discovery interface we have also addressed in a talk back in May, I think, at the AutoSAR Open Conference. So we proposed how this could be integrated into some IP service discovery. And now we will look at the northbound and the southbound interface. The northbound interface, what it basically does, it offers a high-level configuration abstraction for managing applications, so applications that are requesting resources from the network. And the example use cases would here be to request a connection and to request certain quality of service properties from this connection. And the thing is that currently we have the feeling that there's no widely used standard for northbound interfaces. I mean, sure, you need topology information at these interfaces and you need a mechanism to reserve resources, but we haven't really seen like a dominating standard surfacing up. So basically what we say, if we want to introduce this into automotive, we need, at least in the automotive domain, agree on a standard for such a northbound interface. And our bold proposal would be to introduce a well-known SUM IP service for that gives you the methods, for example, to do these resource reservations. And the parameters you need, that's very similar to the manifest we've learned of in the talk before. So you can extract this from things you already know, like you know your addresses, how to identify your traffic flows, you know your bandwidth, you can annotate latency requirements, so that you can integrate into this SUM IP interface. This is then all handed to the SDN controller. The SDN controller does internal computations, finding the best path, and then basically it's up to the SDN controller to configure the actual resources in the network via a southbound interface. What does a southbound interface do? It abstracts the implementation details of the network devices. So here, for the connection we requested before, we now reserve an actual path. Here we know which path in the network we make, and we can also make concrete resource reservations along this path. And what helps us to implement this abstraction is data models. So very briefly, you basically, instead of having proprietary register addresses, you now basically switch to standardized parameter identifiers for your switch configuration, for example. And Yang is a data modeling language which is prominently used for creating such data models. And as we've learned yesterday from Janos and also saw today, there's many models already available from the IEEE, from the IETF you could take and use here for a southbound interface. The next thing is management protocols, and very briefly, basically, if you have your data models, you can create instances, so actual configurations, and the data models basically help you to communicate this back and forth between the controller and the managed devices. And there's a couple of protocols to choose from. So there's originally netconf, then there's restconf, coreconf. They all have different properties, and out of those, we found that coreconf is a quite well fit for constrained embedded devices such as automotive Ethernet switches. And this is also why we took coreconf as a POC, as a demonstration example. So basically, we took our Electrobit Zoneo switch core, which is a highly optimized classic AUTOSAR stack for automotive Ethernet switches, and basically took this and added a coreconf agent, a coreconf server here in the automotive stack on top of TCP/IP. It's using UDP. And if you look at the resource consumption, so we took an Infineon 88Q5152 switch, and the resource consumption of this prototypic implementation were basically 10% of the ROM we had available and 5% of the RAM. So this gives us quite a good confidence that you could use coreconf in actual automotive use cases. All right, now Carsten will tell us about.
Yeah, and then what about the central controller? We had this magic thing that is going to look over the configuration. And yeah, in the classic SDN, this is the all-powerful and all intelligent instance that is creating a new configuration. However, for automotive, this might look a bit tricky. It will need a lot of resources, so we are not sure if we can establish that within the vehicle. And there's also timing constraints, safety constraints. It's risky, so we don't really want to reconfigure the network when the car is running and we are maneuvering. So there are constraints, and it's not totally sure how this can be done in automotive. But as your desk already said, there is intermediate steps, and I think there's at least two use cases that make it very valuable. One is just the fact that you have a single place where you can do the updates. So when you come up with a controlled, OEM-controlled software update where lots of things are changed and there has been a decision that the network structure shall be changed, you have a single instance that you can put the command to. So this is for practical reasons, I think, an advantage. You can download the new network configuration to the single point, and this one will then distribute it over the network. You could even have some local intelligence that knows about variations of this very car, so the update process might be simpler. But then there's also the second use case, which I think is in the connection of SDVs very important. What is when a new service comes? So the customer wants to purchase a new service, and I would also say it like Sodesco said, Yodesco said, I want to have a manifest that the service explains about the resources. And then I need to make a decision locally on the vehicle. Do I have the resources? Is there enough RAM? Is there CPU resources available? And are there network resources available? And only if this check was positive, I'm going to download this thing. Now let's look at how do we activate it actually. So now a new software is there that wants to take up resources that was not planned before. And our proposal for an intermediate and robust automotive available algorithm would be that I have traffic classes forward. No, traffic class is the wrong way. It has a meaning, but we call it forwarding classes, which is just a pre-reserved channel in the network which is not full when you purchase the car. So you have something like 4 free of these predefined channels. And with the manifest, the SDN controller can do a very simple decision. It can say, okay, how many services do I have in a certain channel? Does this new service fit to it? Yeah, it has been checked before, it fits to it. And when it's being activated, then I'm assigning it to one of these predefined channels. So the task of the SDN controller is a lot simpler than in the IT world. It is just adding a new service to a bunch of services in a certain forwarding class. And then it will practically make this decision, okay, this service goes to this forwarding class, informs the end nodes about it, and on the end node, then I have to configure a shaper that makes sure that the application is actually talking to this forwarding class and is doing its bandwidth limitations as it is described in the manifest. We don't expect so much that this will happen a lot in the classic AutoSAR world. So the predefined, pre-calculated, safety-relevant stuff that has been calculated and configured by the OEMs before is on the classic AutoSAR part. And on the adaptive part, on some Linux services, you can do this shaping tricks and introduce a new service. And on the network side, I can have a policy that is actually looking for, okay, this node is not talking more than was agreed in this service manifest. And the network nodes itself are not reconfigured at runtime. So the reconfiguration risk is not there. There's just this adding of services to predefined forwarding classes. And we think this is a way that we could go for also doing runtime reconfiguration because we are using resources that have been reserved and we are just adding them to the reserved resources. And we also tried how this could work, and there's a demo that we want to describe.
Yes, so this is the demo we did. So basically, we wanted to show how the network can be dynamically reconfigured, and by assigning a new forwarding class to a time-critical service. And what we basically have to start with, we have this network here. We have a couple of hosts. We have an SDN controller, and we have switches that interconnect these hosts. The switches run our EBSUNEO switch core firmware with a CoreConf extension we mentioned, and the hosts are simply a Linux-based host which run EBCorbus ADG-COM as the middleware. And the use case we want to show here is basically the transport of a time-critical video stream from host A to host B in the presence of interfering traffic from a host D, which also goes in this direction. We will run this basically the evaluation twice, once without any quality of service means as a baseline, and then we basically apply our software-defined networking approach and compare those two. So the software-defined networking approach is actually using our proposed SUM-IP service discovery extension. So when we start, host B wants to subscribe to this video stream, and it basically sends out a find, basically telling the video server about its bandwidth needs for this video. The server then answers with the offer, basically stating what it can provide in terms of video bandwidth. The client checks this and then subscribes, and can also state a maximum desired latency that it expects from this video traffic. The server then takes all this information it has now about the service request and basically states this to the SDN controller as an abstract resource reservation request. The SDN controller rolls this out, in our case via CoreConf. Here the slides are, there's a slide error, so it doesn't really talk to the network devices. In our case, it talks to the end stations, as Carsten explained. Then the network devices, in this case, basically say the resource reservation was successful. The SDN controller propagates this back to the server, and the server can then acknowledge the subscription. and also then the applications can communicate. Now, for the results, on the left-hand side, you see the baseline, so we don't have any quality of service here. We get some latency distribution, and we also measured at the first switch that we have about 10% frameless for the time-critical video traffic stream, and on the contrast for the SDN-controlled use case where we basically moved dynamically at runtime the time-critical traffic to a privileged forwarding class, we see a different latency distribution for the beta, and we also were not able to observe any frame loss at any of the switches in the network. And I guess what's left is to conclude, and that's up to Carsten.
So we think that we have all the pieces together, and we think that we could go ahead. So there is a northbound interface proposal, which is Automotive, based on Sun IP. There is a proposal for a very simple and robust network controller that we think could be used in an automotive environment. We have the TSN based networking that can be used for creating these forwarding classes, and we can create a central contact point. And on the southbound interface, this is well-established protocols available. We tried it out. CoreConf and Yang are just working, and they don't even eat up so many resources. So we even think that this could be done in the interpretive way, that you are having an abstract interface, Yang-based, that you use to talk to the switches. So thank you very much, and that's the end of our presentation.
Thank you, Carsten, Daniel, for this rich presentation. Now that brings us to the final round for the question and answers. So I see here there is, okay. So I will let the audience choose. So please feel free.
Okay, thank you very much for the presentation. Really interesting. So I would like to come back to the southbound. So you mentioned CoreConf Yang. I know it's a huge discussion about that. But yeah, it's available in a way, but it's not available, for example, in the software stacks we are used to use in the automotive, like AutoSAR and so on. And I see that you have proposed some IP for the northbound. What do you think about some IP? Because it's not available, kind of some IP solution for the southbound, which is available in AutoSAR or something like that, and can be also used. So have you explored on that?
Yep, we were envisioning this interface as being totally standard compliant. So we were using this IT standards as an experiment. We are not claiming that this is the last word, but this is something that can be done. You just use CoreConf and Yang and ignore automotive things like some IP. But of course, we could have solutions that are some IP based for the configuration also. But here we have the nice property that we just need to look into the standards to see how it works. And we haven't found a lot that was missing there. So I think TSN-19 is there to discuss things that are missing. But I'm saying boldly, something like 80% of the parameters that you typically need are already standardized and can be used. So we are having a totally independent interface, which is CoreConf, and exposes the switch to the network with this standard, independent of there is an issue running or whatever.
Okay, thank you. So we'll need kind of a profile of this for automotive and some standardization so, in AutoSAR too.
And we need a discussion if this is a way to go.
Okay, thank you very much.
Thanks so much for the talk. I really liked your use of some IP, obviously. But the question I think that we're dancing around is the question of security. I think it's well established that if you reconfigure your network, you actually need a better security to make sure nobody reconfigures the network than you need security on your actual data communication. So how do we solve the authentication problem or the authorization problem? Which server is actually allowed to change which element? Are we not increasing our security problem that I'm not sure we've solved all elements of already? Are we not increasing that and opening up a huge door here?
Yeah, I'm not sure about that because you already have the security problem, so you need to protect the switches already now. And maybe it's simpler when you have a single instance talking to the switches. So if you decide that this SDN controller is the only one, then the only thing you need to do is you need to authenticate that a request comes from the SDN controller, which might be a simple way of doing security. So the switch would refuse any kind of reconfiguration requests that is not authenticated to come from the SDN controller. So maybe this is even a simplification of the security problem.
I think you are setting yourself up for a repair problem in a shop when exchanging the server. But okay, I think we agree to disagree, maybe.
Okay.
Okay, let me continue. On slide 13, you have shown the overall architecture. And there's a frequently topic of discussion concerning young models. So we see that we have individual network devices, the switches, but the overall problem is, let's say, an out-of-house system problem, the distributed system, a network management problem. So that SDN controller has actually two roles. Yeah? He is responsible for the individual network devices and the end systems. So this is let's say, the network device management, but also he's doing network management, yeah, because these TSN streams are end-to-end communication services, end-to-end objects, and so on. So the question is always, for that network management, what kind of young modules are required, or what kind of young models? Yeah, these are mainly the topology models. Yeah? So you would have a young physical level topology model. You would use a young model for the active topology of an Ethernet network, a young model for the VLAN, and of course also you need a communication matrix. You could also use a young model or a forwarding path. Yeah? So it's not only the individual network element which is modeled or abstracted by young, it's also the network-wide parts. Yeah? And I think Janusz could agree. Yeah, that's the way.
I also agree, yeah. Thank you.
Okay. It's basically a similar direction I'm going to. So I'm from Airbus, so not a real car maker. The point is, first of all, I'm happy that you're using standards like Young, and this is just because we have to serve our needs from different market segments, most likely. So the question I have is regarding the verification, validation of a configuration. So if I understand it right, you plan and verify those configurations offline before you roll them out. Is this correct? So you use the basis, so the configuration you define, which ends up in young model usage, etc. So you use this as a basis for verification before you transfer to the car. Is this understood correctly? Or do you do this also intend to do on the fly inside the car?
No, the idea is, especially of this first step, that you have pre-validated configurations that have this reserve of the fixed defined forwarding classes. So this is pre-verified.
Okay, then we're on the same page. Yeah. That's good. Thank you.
Hi, Harry Palmer from Infineon. I have a question. Maybe you already answered it, but I just want to get a bit of, from an abstraction point of view. You talk about having the YANG models for the switch parameters which are defined. So where does every switch vendors will have a different register map and whatever, right? So where does the abstraction layer reside? Is it in the host or is it in the switch itself in terms of abstraction?
Now in this proposal it's in the switch.
It's in the switch.
But this is not technically not necessary, so you could have other models. Okay. But in our experiment, we had this agent in the switch, which was doing the YANG input directly and translating it to the registers of the switch.
Thank you.
Thank you very much for the great presentation. I really like it. And two reflections. One, first to Albert, this is how we started in QCC, arrows only to the bridges, but we have introduced arrows to the hosts because the host has a NIC, so it's part of a network. So actually the SDN controller, CNC and TSN terms can configure the NIC. So we are one step forward. And it's QCC that has introduced the models for TSN, and 802.1 QDJ went beyond and completed, because we found gaps, completed, as you said, these Yang snippets and Yang models, so you might consider taking a look. And you mentioned in your first response that I was happy to hear the good coverage of these Yang, but if you find gaps, I would suggest to contribute. Please come to 802.1, we want to address the needs. So let us know if anything missing.
Thank you.
So thank you all. And also I want to extend a huge thank you for all our brilliant speakers, and also ask them to stay here next to the floor, and also ask the audience, feel free to, for discussion, any extra questions for them. And the lunch, and we arrived for the lunch break, and the lunch will be served just right here outside. So thank you all, and we will continue at 2 p.m. See you soon.
Thanks.